Thanks, Christina. Good afternoon, everyone. My name is Steve Hale. I'm a Senior Engineering Manager here at CAE Associates. Today I'm going to talk about the Workbench Acoustics ACT tool. I'd like to discuss what the tool is, its features and applications, and then I'll go through a live demo. This is part of the CAE Associates Ansys e-learning series, where we introduce some interesting functionality of Ansys and Workbench, and the idea here is to demonstrate some of these capabilities so that you can maximize your software investment. The time duration of this webinar will be between 30 and 40 minutes. Everyone is muted, and so if you do have any questions, just type those into the chat window, and I'll try and address some of those at the end of the webinar. Okay, moving on. Let's get to page 2. Just give you a little introduction of who we are, CAE Associates. We're an engineering consulting firm here in Middlebury, Connecticut. We specialize in finite element analysis and CFD analysis. We're an Ansys channel partner, and we've been a channel partner since 1985. We have a very extensive website. We have a resource library on that website where you can access all of our webinars, papers, tech tips, macros, case studies. It's searchable, so you can find whatever you need there. We also have a blog that we write about every week, and the idea there is that we share our insights. We have a lot of collective experience here at CAE Associates, and we share our insights into engineering methods and techniques. We do teach many courses here at our Middlebury office, Ansys courses. If you don't know what course to take, you can check out our CAE University link, and that will help guide you through the process of making that decision. You can also check out our training calendar and find out what courses are upcoming. The e-learning series videos, all of those have been recorded. This one is being recorded as well, and you can access that on our website directly in the resource library under webinars, or you can go to our YouTube channel and find it there. If you are licensed PE in New Jersey or New York State and you'd like to obtain a PE credit for this, you can do so. Just attend the whole webinar, participate in the polls, and complete a short survey at the end, and you can receive a PE credit for this. Okay, moving on. As I mentioned before, I'd like to talk about, introduce you to the Workbench Acoustics ACT tool, talk about what it is, go through briefly some of the applications and features, and then spend most of the time on a live demo of the product. This is an image, by the way, of the live demo that I'm going to show you. This is a speaker inside of a speaker cabinet, and then on the right we have an image of the sound pressure levels in the surrounding acoustic domain. All right, so what is Workbench Acoustics ACT? Workbench Acoustics ACT is a application customization tool that's been added to Workbench Mechanical that gives you access to the acoustics features in the full Ansys solver. So it allows you to define acoustic properties. You can apply acoustic boundary conditions and loads. You can assign acoustic structure interfaces and post-process acoustic results. You can look at things like acoustic pressures, acoustic sound pressure levels, velocities, and so forth. Some of the applications. Now, acoustics, in case you're not familiar, it's the study of the generation, propagation, absorption, and reflection of sound pressure waves in a fluid medium, so that can be a liquid or a gas. Some applications for acoustics can be noise reduction in buildings and elevators, machinery, vehicles and mufflers, underwater acoustics. You can model the design. You can use it to help design speakers, speaker housings, acoustic filters, other devices. This image down at the bottom is a muffler, and this is a fringe plot, contour plot of the sound pressure levels within that muffler. There are many acoustic menus that are added with this ACT tool. So these look very similar to what you'll see in standard workbench mechanical. And you can see on the left, for example, we have excitation options, so we can assign wave sources such as plane waves, dipole waves, speaker wave sources, etc. We can assign a mass source to get a flow rate, normal surface velocities. We can apply static pressures under loads. We can assign acoustic pressures directly under boundary conditions. Also assign things like attenuation surfaces, impedance, boundary conditions, etc. Under results, that's where you can specify the results you want to view after the solution is solved. So typical results to look at would be things like acoustic pressure as a contour plot, or acoustic sound pressure levels. We can also look at acoustic Farfield information. So this is acoustic pressures or sound pressure levels outside of the acoustic domain. And the same thing with a Farfield microphone. So that the microphone is a location that you specify in space outside of the domain where you want to get the time or the frequency history of the sound pressure levels or the acoustic pressure. With this tool, you can model the fluid medium and the surrounding structure. You can run modal, harmonic, or transient analysis types. So with a modal analysis, you would look at things like the acoustic modes in an acoustic cavity, or compute the mode shapes of a vibroacoustic system. Harmonic analysis is what you typically use this for. So this is where you would look at the acoustic response to a harmonically varying acoustic load. With a transient analysis, you can get a solution, acoustic solution, to a non-harmonic type of load in the time domain. And as I mentioned before, you'll typically look at pressure distributions, sound pressure levels, particle velocities, and so forth. You can also look at scattering of the acoustic waves, diffraction, transmission, radiation, attenuation, dispersion. You can model an uncoupled acoustic analysis, which would model only the fluid domain, and it would ignore any fluid structure interaction. So the waves would simply reflect off of any boundary you might have. Or you can model a fully coupled acoustic structure system. So in that case, you would have if it's a harmonic analysis, you would run the coupled harmonic analysis that would include both the structure and the fluid, and they would interact with each other. So the pressure would help to the pressure would interact with the displacements at the boundary of the structure. All right. I'd like to bring up the first poll question, and I'd like to know what your potential application might be for acoustic analysis. So I have a couple of options here, multiple choice. Would you use this to analyze noise reduction in machinery or engines, noise reduction in buildings or elevators, noise reductions in vehicles or aircraft? Would you use it to design speakers or acoustic filters, or are you not sure, or simply don't? Or is it some other application? So I'll give you 30 seconds to answer that, and then we'll take a quick look at the results, and then I'll move on to the demonstration. Okay. So most of you aren't sure what you would use this for, and about 11% would use it for noise reduction in machinery or engines. But there are many, many different applications for acoustic analysis. So hopefully by the end of this webinar, you might have a better idea of what you could use this for. Okay. Moving on to the demonstration problem. So this analysis involves the acoustic, structural acoustic interaction of a speaker with the surrounding air. And the idea here is to look at the pressure, the acoustic pressure, and the sound pressure levels in the air at different locations. So this is a quarter symmetry model. All right, so we're just modeling 1/4 of the speaker and the speaker cabinet with all of its internals, and then 1/4 of the air surrounding that. And we'll do a harmonic analysis. So we'll sweep through a couple of different frequencies, and we'll look at the acoustic response at those two frequencies. The forces in this case are exerted on the voice coil of the speaker, which causes it to move, and then that interacts with the surrounding air to produce sound. You'll notice on the outermost region of this model, we have a TET mesh that's gray, and that is modeled as a perfectly matched layer. And the idea of this PML layer is to absorb the outgoing wave. So it represents the case where you have an infinite domain of fluid, or in this case air, surrounding the speaker. All right, and then on the right we just have an image of the sound pressure level that was solved for. All right, so let's take a look at Workbench here. We have the Workbench project page. The way you would set this up is you would simply go to harmonic analysis in the toolbox, drag and drop that directly onto the project page, and that's how you would start. You'd set up your geometry first, so you can import that from your CAD tool, or you can bring this up, or you can do some of the geometry processing within Design Modeler in Workbench. One of the nice tools or features of Design Modeler for this purpose is you can use something called the enclosure tool. So if I go into Tools, Enclosure, that basically what it does is it creates a solid body that overlaps your structural body, and it subtracts the structural body from the solid body that you create. So that allows you to create the fluid domain that surrounds your structure. What you need to do once all of those bodies are created, so we have a series of bodies that are used to define the air domain around the speaker cabinet. All right, so I'm highlighting those now. And this is split up for the purpose of getting a reasonable mesh transition between the structural bodies and the fluid, in this case air bodies. Now what you'll notice here is down at the bottom, we have one part with 36 bodies. We need to make sure that the air bodies or the acoustic bodies share nodes with structural bodies in order for the displacements in the structure to be converted into pressures in the acoustic domain. All right. Now, once the geometry is all set up, we can import that into mechanical. You'll see in the toolbar up at the top, we have a line of menus for the Acoustics ACT tool. The first thing we need to do here is insert some symmetry items to simulate the symmetry boundary conditions on the two symmetry faces. So I insert a symmetry folder, right-click, insert a symmetry region. So this is identical to the procedure you would use with a structural analysis. Symmetry region. Now I have some name selections that I've defined for the symmetry faces. So I have symmetry on the XY plane here, And that symmetry direction is going to be in the global Z direction, along the global Z axis. I can insert another one then for the other set of symmetry faces. So that's symmetry on the YZ plane. And the direction of that symmetry would be in the X direction, the X axis. Okay, so that's defined. If we take a look at mesh now, I just want to talk about this for a minute. Vast majority of these mesh controls that we have in here are used to define the sizing within the structural body. They need to have a relatively fine mesh to capture the modes in the structure. Now, for the acoustic domain, we have a certain size criteria that we should be using, and specifically, what you need is you need to have at least 6 elements per wavelength if you're using quadratic element types. So, what we're going to do here is we're going to sweep through from 700 to 1,000 hertz frequency, and so the maximum element size should be the speed of sound in the air, that's 343 meters per second, divided by that highest frequency of 1,000 hertz. So that's 0.343 meters per wavelength, and we need 6 elements minimum per wavelength. So that gives us 0.057 meters per element. So that's what I have here for these outer acoustic domains. I have it says 57 millimeters. Let me change the units to meters. So 0.057 meters there. I'll mesh this up, and you can see what this looks like. Now, as I mentioned before, this is a single multi-body part. All these parts have shared faces, so that when it meshes this up, if you look at this closely, we have nodes that are shared between the air and the structure, in this case, the speaker itself. Okay, and that goes all the way around the outside of the cabinet as well. Okay, now how does Workbench know which is an acoustic body and which is a structural body? Well, by default, it's going to be structural. But to define it as an acoustic body, we can go up to the Acoustics ACT menu here for acoustic body, insert an acoustic body. And then under geometry, we can select these acoustic bodies. Now, if you recall, the outermost body needs to be a PML body, a perfectly matched layer, which is used to absorb those outgoing waves. So that needs to be defined separately. All right, now by default, the mass density, the speed of sound, reference pressure, reference static pressure, those are all defined for air room temperature. If you want to, you can change that to be anything you want. So if you want it to be a fluid, some other gas, you can easily change those properties. You can also assign viscosities for fluids. This, you'll see down here, there's an item called Acoustic Structural Coupled Body Options. By default, it's uncoupled, meaning that it will not convert those displacements into acoustic pressures. If we wanted to do that, we have to change this to coupled with unsymmetric or coupled with symmetric. The symmetric algorithm is a newer feature, newer capability that simplifies this whole process. It uses less overall memory and less time to solve the analysis if you use this symmetric algorithm. So that's the recommended technique nowadays. So couple with symmetric. Now we need another acoustic body for that outermost PML region. Go back to acoustic body. Insert another one. Pick that outermost body. That all needs to have the same properties as the inner acoustic bodies, so I'll keep those the same. That, again, has to be coupled with the symmetric algorithm. Even though it doesn't interface directly with the structure, if you have one region that's coupled with the symmetric algorithm, all of the acoustic regions have to be coupled with the symmetric algorithm. The perfectly matched layers now, that has to be turned on for this region. The other thing we need to do for this PML region to absorb the waves properly, there's one more step. We have to insert a boundary condition for acoustic pressure and just specify acoustic pressure of 0 on that outermost boundary. So what I'm going to do here is pick those faces. Now those all have 0 pressure assigned to them. One thing I haven't done yet is I haven't specified the frequencies for the harmonic analysis. So I want to go back to analysis settings. The minimum frequencies can be 700. I'll go up to 1,000. I'm going to sweep through those frequencies. I can use as many solution intervals as I want. So in this case, I'm just going to use 2. And that's going to solve actually a frequency of 850 and 1,000. So it uniformly distributes those frequency intervals. Okay, under damping controls, we want to specify the damping for the structural components. So this constant damping is going to be applied to those structural components only in the harmonic analysis. All right, now how do we tell it that we want to have a acoustic structure interface in this model? The way we do that is we go back to boundary conditions. Boundary condition drop-down menu and select FSI interface. That stands for fluid structure interaction, or in this case, acoustic structure interaction. And we already have a name selection defined for this. So I'm going to go to name selection, FSI, and you'll see, I've got to change one thing here. Okay, so you'll see dark blue, that's showing the acoustic FSI interface all the way around the speaker, all the speaker faces, and the outer surface of the cabinet. All right. Next thing we need to do is we need to apply the harmonic load. This is just going to be a very simple vertical force applied to the voice coil. So in that case, I can just right-click and insert a force directly to the structure. The voice coil is this body here. So I'm going to pick one of the faces on that voice coil, give it a magnitude of 1 Newton. So that'll be a harmonically varying force of 1 Newton on that voice coil face. You'll see it's vertical by default in this case, but I can change that direction if I wanted to. Okay. Let me insert a couple of results, and then we can take a look at those results. So we'll look at acoustic pressure. We'll look at acoustic sound pressure levels. Those can be scoped to any bodies that we want. By default, it's just going to give us the pressure levels and the sound pressure levels for all of the acoustic bodies. So an acoustic pressure, what I'll look at is pressure in, say, all of these acoustic bodies. Sound pressure levels, I can look in the same bodies or different bodies. The other thing I could do, let's say I wanted to insert or take a look at some Farfield pressures. I could do that by inserting a Farfield microphone. And what this is going to do is allow me to extract those pressures as a function of frequency at a location outside of the acoustic body. So if I want to look at sound pressure levels, I leave the result at sound pressure levels. I have to give it a position in space and a sphere radius. So this, you'll see this dot, this blue dot up at the very top. That's the location of the microphone, and that's defined based on an angle from the global y-axis, from global z-axis, and then a distance on that sphere. Okay, and that reference RMS sound pressure level is used to give you the correct decibel calculation. All right, so let's take a look at the results quickly. I'll open that up. Okay, normally I would have this open, but I had to restart Workbench. All right. So we can look at acoustic pressure. This is the acoustic pressure response in the air for these acoustic bodies. I can look at the acoustic sound pressure level. All right, this pressure, by the way, if you look in the upper left, you've got it, I'm showing it currently at 1,000 hertz, but I could look at the other frequencies that I saw for as well. And I'm looking at these pressure levels at a phase angle of 0. I can display this for any phase angle that I like. Now I'm looking at the sound pressure levels in the same acoustic domain. This shows 0 hertz, but actually if you look down on the lower left, it's at the last frequency, so it's actually at 1,000 hertz. The other thing I want to show you here, see where it says acoustic time frequency plot. This is the graph of the amplitude of the response, in this case the pressure, as a function of frequency, and the associated phase angle at which that maximum occurs. So I'm looking at the I'm trying to find the maximum pressure, acoustic pressure, in a specific body, air body, acoustic body, and I want to get the phase angle at which that max pressure occurs. So if I look at the 1,000 hertz solution, which is all the way to the right, that phase angle is about 71 degrees. In this case, negative 71. And what I can do, see, I have an item for acoustic pressure 2. And I'm looking specifically in this acoustic body. So I've extracted the results at a phase angle of 71 degrees. Now in the acoustic time frequency plot, it's shown as negative 71, but you have to take the negative that to get the maximum pressure result. All right, and from that you can apply that as a sweeping phase, and you'll see you get the maximum pressure contour shown on there. We also have the acoustic Farfield microphone. So remember, I inserted that microphone, and I can look at the sound pressure level as a function of frequency at that location outside the acoustic domain. There's also an acoustic Farfield item, and that's very similar, except in this case, you're creating a spherical path outside. You can also look inside the acoustic domain. And in this case, I'm looking at sound pressure level. I can look at other results, but I'm looking at sound pressure level in this case as a function of angle on that sphere. Notice in the lower left, that sphere radius is 1 meter or 1,000 millimeters. So you have to specify that as well. Okay, let me go back to the slides. And I just have a couple more slides here and another poll. So there are many acoustic features that I didn't cover in this presentation. It's a very, very powerful tool. You can, for example, create and model a non-uniform acoustic medium. That can be a function of temperature or static pressure. You can solve for acoustic scattering. So this image down at the bottom shows acoustic scattering around a submarine. You could apply or assign bulk viscosity to model viscous losses in the fluid. You can input mass sources, impedance sheets, normal velocity boundary conditions. You can do near-field post-processing. I showed you some far-field post-processing in my example. You can also assign excitation loads as wave sources, external planar waves, monopole wave, dipole sources. All right. My second poll here, do you think this tool might be useful in your work? I'll just give you about 30 seconds to answer that. I'd like to get an idea if you think this might be a helpful tool for you. And then I just have a couple of wrap-up comments. Okay, so we have some good responses here. Most people think that it would be somewhat useful. So that's great. We do encourage you to use this, and I'll tell you how you can get a hold of it. The acoustics analysis requires a license of Ansys Mechanical or Multiphysics. You have to have that. If you do have that, you can download the ACT tool directly from the Ansys customer portal, and that's under the ACT extension library. It's right there on the front page of the Ansys customer portal. When you download it and unzip it, it has some documentation, including some training materials. So there are some instructional slides and some workshops that are included in that download. All right. Let me check to see if there are any questions.